Okay, here's our start of our um, section on the preparation and reactions of acid chlorides. So the acid chloride is our most reactive of the carboxylic acid derivatives. And this reaction here that's on the screen, we're going to see quite often, or at least use quite often in our synthesis reactions, because we can hydrolyze any of our carboxylic acid derivatives to the carboxylic acid. That can happen under acidic or basic conditions, usually aqueous, no, not usually, definitely aqueous conditions. And then we can do the reaction that converts the carboxylic acid into an acid chloride. And when we looked at our reactivity tables before the break, we saw that once we had the acid chloride, we can easily convert that into any of the other carboxylic acid derivatives. So this reaction uses thionyl chloride, which is a species that or reagent that we used back in Org 1. If you remember, we used that to convert an alcohol to a alkyl chloride. And it's often used in the presence of pyridine, so PY for short. Pyridine, of course, is this molecule here. It's used as a base, and in the preparation of acid chloride, you often use it also as a solvent. And you see that we produce this hydrochloric acid, and that's why the pyridine is added. So let's go on to a blank sheet here, and I'll start to talk to you about the mechanism. So we take our carboxylic acid and we react it with the thionyl chloride. The thionyl chloride has got that very electrophilic sulfur atom, and so we get this nucleophilic attack at the electrophilic sulfur atom, and we pop the electron density up there. And again, sorry, occasionally it does that little line there. I think I'll get a bit better at avoiding that, but I must be putting too much pressure down. But again, like in the case for making the alkyl chlorides from alcohols, all we're really doing here is we're trying to convert this into a better leaving group. So we have an intermediate like this, and we have a positive charge on that oxygen. And this is one way to represent the mechanism. The textbook shows a slightly different way. But what I wanted to point out here, and I'm going to draw pyridine, is that we often add pyridine to these types of reactions. So not just this preparation of the acid chloride, but also in a few more of these carboxylic acid derivatives reactions, especially the ones with acid chlorides. And at this stage, the pyridine could act as a base and remove that proton. So what we're going to do from now on is if pyridine is added, we're going to deprotonate before anything else happens because it's there present as a base. And it really does help this reaction work a lot more efficiently when you use pyridine in the presence of the thionyl chloride. The next step then is after we do this, we end up with, sorry, I automatically put in my equilibrium arrows. We put in, oops, let me get back to that slide. Kind of moves on me. Okay. We've got this intermediate here. And we reform the oxygen sulfur double bond and kick out a chloride. And now we're set up where we've got that chloride around, so it can act as a good nucleophile here. And we've also got a good leaving group. So we get nucleophilic attack at this electrophilic carbonyl carbon. Form our typical tetrahedral intermediate. So again, this is still just another example of the acyl or the generic or general acyl substitution reaction. We reform the carbonyl and kick out the leaving group. Here it's got to be a pretty good leaving group or pretty special leaving group to beat chloride as a leaving group, and it is. So if you follow the arrows that I've drawn there, what we end up producing is our desired acid chloride plus sulfur dioxide, and then another chloride. Of course, sulfur dioxide is a gas, and gases are the best kind of leaving groups because they don't just leave the intermediate, they leave your whole reaction flask. And that's how we produce the acid chloride. So this is a reaction. Again, it illustrates some of those points where we have from the general nucleophilic acyl substitution reaction, where we have a few different stages in those reactions with proton transfers and the like. So switch slides here again and talk about some reactions of acid chlorides. We've got the general reaction shown here, and in that general reaction, we see that the nucleophile will replace the chloride, and we'll have a hydrochloric acid byproduct. We often run these with pyridine, but the first one we're going to take a look at is the hydrolysis. You don't usually add pyridine when all you're doing is trying to hydrolyze something. And this is a reaction that you don't tend to do that often, but it is a reaction that you want to avoid. So one of the issues with acid chlorides is that they're sensitive to moisture, and there's a lot of moisture in the atmosphere, with the general humidity. So acid chlorides have to be handled with a bit of care. Typically, you would not leave them hanging around too long. You would take the acid chloride and do the next reaction. If you've ever worked with a bottle of an acid chloride, you can tell it's a reactive substance. You actually see some fumes of hydrochloric acid being produced if it comes in contact with water. So let's take a look at this mechanism. Should be able to complete it on the slide here. So we have this carboxylic acid, sorry. We've got our acid chloride in water. So we get nucleophilic attack at the electrophilic carbonyl carbon. In this case, we've got no added base, so we don't deprotonate at this tetrahedral intermediate. We reform the carbonyl and kick out the chloride. I shouldn't have the equilibrium hours there, sorry. Went into autopilot. Now we have a carboxylic acid that's protonated. And then the last step is a proton transfer, and we use water as the base to remove that proton, and we produce the carboxylic acid. So there might be a couple of times when you want to do this reaction, but typically this is a reaction that we really want to avoid. So let's move on to some more useful reactions of carboxylic acids, of acid chloride, sorry. And that's using the acid chloride in the synthesis of esters. So here is the reaction between an alcohol and the acid chloride to give us an ester. And these are often done with pyridine in the reaction mixture. So let's take a look at this reaction. And again, hopefully you're starting to see the trends here, but we've got the acid chloride, we've got our alcohol, we get, lo and behold, nucleophilic attack at the electrophilic carbonyl carbon. We have our tetrahedral intermediate. We got pyridine present, so let's use it to deprotonate at this stage. Now we're set up. We're reforming the carbonyl. We'll kick out the chloride. And we form the ester that we desire. So again, it's a nucleophilic acyl substitution reaction. We've got our nucleophilic attack first, followed by a proton transfer, followed by loss of leaving group. So just like we did in that previous section, section 20.7, there are 3 different places where proton transfers can occur. Here, it just happens once, and it happens after the nucleophilic attack. All right, so the next reaction of acid chlorides we're going to look at is the synthesis of amides. And typically you don't add pyridine here, mainly because, especially if your amine you're using is cheap and readily available, you just need 2 equivalents of that amine. So in this example on the screen here, it's 2 equivalents of ammonia. And that's relatively cheap. It's really cheap, actually. And so that's what's used to do the deprotonation. As you go more advanced and maybe start to think about using a primary amine or a secondary amine, you may not want to use 2 equivalents. So we've got the same kind of reaction mechanism going on. I'll do it on the next slide. But should see that this is starting to get a little bit repetitive. So we have our acid chloride. Let's just do it with ammonia. First step, nucleophilic attack at the electrophilic carbonyl carbon. Get our tetrahedral intermediate. We have a protonated species there. And then we do deprotonation of this intermediate. Because we have that added base already, followed by reforming the carbonyl, kicking out the chloride, and we end up with the amide. Let me redraw that so we don't have that weird line on it. So we have the amide, and the reaction mechanism is the same for having a primary amine that will give us a secondary amide, or where do we have a secondary amine that will produce a tertiary amide. So that's the reaction of the carboxylic acids, or the acid chlorides, to give us the amides. Let's take a look at some reduction reactions. The acid chlorides can be reduced with excess lithal. Remember, lithium aluminum hydride was our sledgehammer reducing agent. So it has lots of hydrides on there, lots of hydrides. Means, of course, it's a reducing reaction, and it will take the acid chloride and gives us a primary alcohol. But as we saw in the previous chapter, we have some acid chloride. We have some ways to modify the reactivity of lithal so that it stops at the aldehyde stage. In this case, one thing I will do on the next slide is I will take a look at that reduction reaction. And we can kind of find out where it differs when we use our other reagent here. So this lithium trialkoxy reagent, the one we looked at in the previous chapter, was tri-tert-butoxy. We used it around the same time we talked about a reagent called dibal, and we used those to reduce esters to give us aldehydes. And it's the same kind of reaction going on here. We've modified our reducing reagent to make it less reactive. And it's a combination of sterics and electronics that's going on there. So let's see. Let's take a look at the mechanism of the reduction with lithial. So our acid chloride, let me try that again. I don't like what happened there. And again. Here's our aluminum hydride. The hydride is delivered, so we get kind of a nucleophilic attack. The electrophilic carbonyl carbon. Get an intermediate with a hydrogen here. We reform the carbonyl and kick out the leaving group. So our intermediate, when we use lithium aluminum hydride, is an aldehyde, but this doesn't stop at this stage. Sorry, I was missing a negative charge from the aluminum, and a second molecule of the aluminum hydride comes, and we get a mechanism identical to what we talked about in the aldehydes ketones chapter, and actually maybe even going back to Org 1. And then the workup involves adding acid or aqueous conditions. Maybe just water will do this too. And we end up making a primary alcohol. We change the color of the pen. But this is the step that doesn't happen with those alternative hydride reagents, like our lithium aluminum tert butoxide. We now have tert butoxide hydride. Sorry, we now have a reagent whose reactivity is being reduced by electronics and also by sterics. So often left out of our discussion, but the byproduct, once the lithial hydride is delivered, is often still associated with as in a complex with our tetrahedral intermediate, or here on the oxygen of the aldehyde. And so just the steric bulk helps to prevent that second addition. So using this allows us to go from, let me write it down here, the acid chloride, it was on one of the previous slides, but stop at the aldehyde stage. Okay. So that's the reagents like the hydride reagents. Here's the Grignard type reagents. So the first one on the slide here, this top one, shows us that if we use excess Grignard reagent, it adds twice to the acid chloride. And we'll look at this mechanism in a second. And the one below is the Grignard version, or the modified Grignard version, kind of comparable to what we just talked about for the reduction. So this type of compound here is called an organocuprate, sometimes known as a Gilman reagent. And the Gilman reagent, again, is modified. So when you get the copper there, the kind of general structure looks like this. This is what bears a negative charge, and the lithium is a counterion. When the copper is present there, it becomes a softer nucleophile. And that's a term we'll talk about in the next chapter, actually, when we talk about some enolates and things like that. But it becomes a softer nucleophile. So it's just not as strong a nucleophile. And in the case of the acid chlorides, it will only add once, and it will stop, in this case, to give us a ketone. So we can reduce an carboxylic acid, we can reduce an acid chloride to give us an aldehyde by using a modified lithiol type reagent. And we can react an acid chloride with a modified Grignard type reagent, the Gilman reagent or the organocuprate, to give us a ketone. So in that, instead of going all the way down to the alcohol oxidation level, we stop at that ketone oxidation level. Let's take a look at the mechanism for the Grignard, but I think it should be fairly obvious what's happening. Our Grignard reagent is nucleophilic, so we get our nucleophilic attack at the electrophilic carbonyl carbon. We produce the typical tetrahedral intermediate because we've added a carbon, and also because we have the chloride there, we have no choice in what happens next. We reform the carbonyl, and the chloride is clearly the better leaving group. And we produce a ketone, and then a second equivalent of the Grignard reacts to give us initially, of course, the alkoxy, and then with our aqueous workup, we produce a tertiary alcohol. So that's the reaction between the acid chloride and the Grignard reagent. And in the case of the cuprate, it's a good enough nucleophile. It's good enough nucleophile to do this step that I'm circling. It's not a good enough nucleophile to do the second addition. So, kind of summary of this, these reactions are shown here. So this looks like quite a complicated slide, but it's essentially the same reaction repeated. So we have our set of 3 versions to create the amides. We can reduce to give us an alcohol or an aldehyde, and we can add a carbon-based nucleophile, so we can add an alkyl group via Grignard. That happens twice to give us a tertiary alcohol, or use the Gilman reagent when it only adds once, and we produce a ketone. And then to the left here just shows you the 2 ways to interconvert between a carboxylic acid and an acid chloride. Now we will do a lot of reactions where we turn things into acid carboxylic acid so that we can turn them into acid chlorides. Okay, so that concludes the section on acid chlorides. Let me come back here and maybe go back just to find a blank slide to talk a little bit about what questions to do. So we're now able to answer in chapter questions 21.6 to 21.8. We're going to take a look at question 21.7 during our office hour on Monday, hopefully. So I'll finish there for this section, and I'll get ready to prepare section 20.9 for acid anhydrides. So let me escape out of this, discard my ink annotation, and stop the sharing and end the meeting.